Welcome to the tutorial on gasometric method in corrosion. I am Dr.N. Gunavathy, Assistant Professor and Head, Department of Chemistry, Nirmala College for Women, Coimbatore. The learning objectives of this tutorial are: at the end of the tutorial, the learner will be able to perform gasometric method in corrosion and to calculate the inhibition efficiency of an inhibitor on metal. The prerequisites are: the learner must have basic knowledge of corrosion, definition, causes and their consequences, theories of corrosion, and mechanism of corrosion. Corrosion is a natural process which reduces the binding energy in metals. The end result of corrosion involves a metal atom being oxidized, whereby it loses one or more electrons. The corrosion manifests itself as a breakup of bulk metal to metal powder. Corrosion degrades the useful properties of materials. Now let us see few definitions of corrosion. Corrosion is an irreversible interfacial reaction of a material with its environment which results in consumption of the material or its dissolution into the material of a component of the environment. It is the natural tendency of the elements of a material to return to their most thermodynamically stable state. According to West. According to Schreier, metallic corrosion is a natural process of the metal going to its oxidized state. Dara defines corrosion as gradual destruction of metal, be an unwanted or unintentional chemical or electrochemical attack by its environment, beginning at its surface. Fontana says corrosion is the destruction or deterioration of metals as a result of reaction with its environment. According to Rajnarayan, corrosion may be defined as the loss of useful properties of a material as a result of chemical or electrochemical reaction with its environment. Corrosion is destructive attack of a metal by a chemical or electrochemical reaction with the environment, says Ulagi. Causes of corrosion: the characteristics of water, chemical and physical properties of water like alkalinity, presence of ions or impurities, temperature, hardness, flow or stability, and pH. Dissolved solids influence the rate of corrosion of metal. Low pH, soft or with primary non-carbonate hardness, low alkalinity increases the rate of corrosion. Presence of bacteria in surrounding also accelerates the rate of corrosion. Characteristics of the metal, electrical currents, or some other factors that influence the rate of corrosion. The consequences of corrosion are reduction of the metal thickness leading to loss of mechanical strength and structural failure or breakdown. When the metal is lost in localized zones so as to give a crack-like structure, very considerable weakening may result from quite a small amount of metal loss. Leaking containers, storage tanks, water, and oil transportation lines and fuel tank cause significant loss of product and may generate severe accidents and hazards. Loss of time in availability of profit making industrial equipments, reduced value of goods due to deterioration of appearance, corrosion products may contaminate chemicals, pharmaceuticals, dyes, packaged goods with direct consequences to consumers. The other consequences of corrosion can also be listed as the perforation of vessels and pipes, allowing escape of their contents and possible harm to the surroundings. Loss of technically important surface property of a metallic compound. These could include frictional and bearing properties, ease of fluid flow over a pipe surface, electrical conductivity of contacts, surface reflectivity or heat transfer across a surface, mechanical damage to valves and pumps, or blockage of pipes by solid corrosion product cause loss of efficiency. Added complexity and expense of equipment which needs to be designed to withstand a certain amount of corrosion and to allow corroded component to be conveniently replaced. Nuclear hazard like the Chernobyl disaster of 1986 is a living example of transport of radioactive corrosion products in water which are fatal to human, animal and biological life. So what is the big impact about this corrosion? It causes damage to materials and lives. It causes damage to the infrastructure, the containers in industries, pipes, even an aircraft, the electronic goods and transportation like car. Some other consequences of corrosion are also depicted here. The plant shutdown, loss of products, loss of efficiency, contamination, and nuclear hazard as stated earlier. Corrosion process, which can be due to a current flow, requires at least two reactions that must occur in a particular corrosive environment. These reactions are classified as anodic and cathodic reaction. Metal oxidation occurs through an anodic reaction and a reduction through a cathodic reaction. It can be seen that at anode, the metallic ion loses electron by the oxidation process and these electrons are used up in the cathode area. And the iron, in the presence of air and water droplet, forms the rust. Monitoring of corrosion is very important in order to avoid the consequences of corrosion. Corrosion is destructive and silent operating process. It poses problem to big as well as small industries. Since corrosion is impracticable to eliminate, the effective corrosion science and engineering lies in controlling rather than preventing it. Practical methods available for protection of metal against corrosion are diverse and they are broadly based on the selection of material, modification of metals, modification of design, use of inhibitors, modification of corrosive environment, modification of surface, etc. These methods can be used individually or in combination. Among the various methods of corrosion control, use of inhibitor is the most efficient and cost effective. Corrosion monitoring techniques are mainly aimed with the objective of diagnosing and controlling corrosion reaction. The corrosion testing and inhibitor effectiveness can be done by non-electrochemical methods like weight loss method and gasometric method. Both the methods are direct measurement methods. Electrochemical methods like potential dynamic polarization method, linear polarization method, which involves the direct current polarization, and impedance method and Faradaic distortion method involving the alternating current electrochemical techniques. Now let us see the gasometric method. Gasometric method gives accurate results compared to that of conventional weight loss method, provided the inhibitor does not react with hydrogen. The hydrogen penetration into the metal is small compared to the total volume of the gas. In this method, the volume of hydrogen gas evolved in the presence and absence of inhibitor are measured directly at a constant temperature and atmospheric pressure using gas volumetric procedures. From the volume of hydrogen gas evolved, the inhibition efficiency of an inhibitor on metal surface can be calculated. The main disadvantage of this method is that they are time consuming. The gasometric setup consists of two parts. The first part of the instrument, that is the reaction cell, consists of a cylindrical vessel of 250 ml capacity with a central joint opening through which the metal specimen can be inserted into the cell by means of a glass stopper provided with a hook. The stopper exactly fits into the central ground glass joint so that there is no leakage of hydrogen gas. It is also provided with a gas release stopper on one side through which excess gas pressure over the atmospheric pressure which builds up when the stopper carrying the metal strip is introduced can be released. Thus, at the beginning of the experiment, the gas pressure of the vessel can be brought to the atmospheric pressure by gently opening the gas release stopper, and the cell is placed in the glass beaker provided with an inlet and an outlet for the circulation of water. The second part of the instrument consists of a gas collector, vertical column tubes made up of standard capacity graduated burette. The vertical column tubes of required capacity can be replaced depending on the volume of gas to be collected. The vertical column tubes are filled with a 20 to 25% sodium chloride solution, acidified with hydrochloric acid, and colored with methyl orange or methyl red. The gas is collected over this solution. The color makes observation of the meniscus easily. The solubility of gases like carbon dioxide, hydrogen, etc. are low in sodium chloride solution, making the measurement more accurate. The reservoir is fitted with a narrow bore glass tube at right angle to provide parallax error during the adjustment of the liquid levels inside the burette and in the reservoir bulb. When the two levels are adjusted to be equal, the pressure of the gas inside the tube is at the atmospheric pressure. As the liquid levels inside and outside the burette are kept the same, from the beginning of the experiment, any pressure correction due to aqueous tension is not necessary. Measurement of the volume of the gas to determine the inhibition efficiency. The mild steel specimens of size 5 into 2.5 centimeter are given a fine mechanical polishing and degreased with the trichloroethylene. The specimens are then stored in a desiccator. The net area expressed is 25 centimeters squared approximately. The specimen is suspended from the hook of the glass stopper and is introduced into the cell containing 200 ml of 1N hydrochloric acid. The temperature is maintained constant throughout the experiment at 30 degrees centigrade and at constant atmospheric pressure. Gas measurements are made for a period of an hour in all the cases. Simultaneously, a duplicate is also performed in all the cases for the verification of the value. Experiments are repeated under identical conditions for inhibitor solution of different concentrations, and the gas volume are measured for duration of an hour. From the volume of the gas liberated, the inhibition efficiency can be calculated using the formula inhibition efficiency percentage is equal to Vb minus Vi divided by Vb into 100, where Vb is the volume of hydrogen evolved in the absence of the inhibitor and Vi is the volume of hydrogen evolved in the presence of inhibitor. We have come to the end of the tutorial. From this tutorial, the learners are able to perform gasometric method in corrosion and calculate inhibition of an inhibitor on metal surface. Now let us check our knowledge that we have acquired through this tutorial on gasometric method in corrosion. In gasometric method, the evolution of dash is measured. A. Hydrogen, B. Nitrogen, C. Oxygen, and D. Carbon dioxide. In an acidic medium, we know that hydrogen gas will be evolved. So, in gasometric method, the evolution of hydrogen is measured. Gasometric method measures dash to evaluate the corrosion rate. A. Mass, B. Temperature, C. Pressure, and D. Volume. In gasometric method, we know that hydrogen gas is evolved, so we measure the volume to evaluate the corrosion rate. Gasometric method is an example of dash method. Electrochemical method, non-electrochemical, thermometric or barometric method. From the experimental setup that we have seen, It is found that it does not involve any electrical connection for the experiment. So therefore, gasometric method is an example of non-electrochemical method. The area on the metal surface that is dealt in gasometric method is anode, cathode, both anode and cathode. We know that in a corrosion process, both anode and cathodic reaction takes place. At anode, oxidation process takes place. Iron loses its electron, and these lost electrons are utilized at the cathode for the liberation of hydrogen gas. Therefore, the area on the metal surface that is dealt in gasometric method is cathode. These are the references that has been used for preparing this tutorial on gasometric method in corrosion. Thank you for listening to the tutorial on gasometric method in corrosion. Thank you.